Welcome everybody to the Ask the Moldflow Experts webinar. As people filter in, we're going to wait just a minute or two for that, and then we'll get started. So please bear with us. Okay, we'll go ahead and get started. So just wanted to say thank you all for taking time out of your day to attend this Ask the Moldflow Experts webinar. Today's topic is one I'm pretty passionate about. There's a lot to talk about when it comes to Moldflow cooling analysis. And the title of today's is What's Best for You? So a little bit about my company, CAE Services. We were established back in 1988. We have the most expert certified Moldflow engineers in the world. We're an Autodesk MIG partner. And, so we sell software, we do training and so forth, along with our consulting business. We've completed some 28,000 plus projects since 1988. So we have a wealth of experience in the Moldflow arena. And if you want to learn more about us, of course, please go to our website. This is a little bit about me. Many of you, I see a lot of familiar names online. A lot of you know me. I've been around for a while, done a lot of Moldflow. I've trained a lot of Moldflow engineers, contributed to trade magazines and presented at the Moldflow Summit in the past. So it's just a little bit about me. So, when it comes to cooling analysis, I'll make a claim that most people don't really know if their molds are optimized, but seconds matter. Sometimes tenths of seconds matter. And if you don't know if your mold's optimized, I think there's some real opportunity there. And a lot of times, I've seen this a lot. We just settle for, well, that's good enough. You look at the images on the right there as they animate. You got a couple of baffles up there, good enough. Or maybe we put a bubbler in the center of that, good enough. But the question that should always be in your mind is, can we do any better? There's a lot of rules of thumb out there for cooling design and so forth, and I think those get followed and have been perpetuated over the years by many mold designers. And oftentimes it is good enough, but again, the question should be, can we get any better? There's always room for improvement, in my opinion. And how do we know until we mold parts, really? So cooling analysis, using Moldflow is one way to take that guesswork out of it. But the question is, what type of cooling analysis should be done? And that's going to be one of the focuses of today's webinar. So our key message here, though, is no matter what type of analysis you do, the fundamentals really don't change. You've got a heat load on a mold, and you've got to get that heat out of there, and you want to do it as uniformly and efficiently as you possibly can. So, but how do we take advantage, rather, of those fundamentals to get the cooling and uniformity and efficiency that we want? As I mentioned, there are different types of Moldflow cooling analysis, and we'll get into those. But cooling design should not be an afterthought. Cooling uniformity and efficiency can be improved proactively and we do that through simulation. So again, the fundamentals don't change, right? It's the way we get heat out of the mold. It's an exchange. It's a heat exchange system. It's a heat exchanger. You know, two modes of heat exchange are conduction and convection. On the left, we have conduction. That's the heat transfer between the two surfaces through a medium, two surfaces at different temperatures. And if you like equations, there's the equation, heat flow. For convection, it's heat transfer between a surface and a moving fluid, i.e. the coolant here, that are at different temperatures. So those are the two modes of heat transfer that occur in an injection mold. And again, we want to try to take advantage of that as best we can. There's the equation for convection. So when we do analysis, there's really two aspects that we look very closely at. One is the uniformity and the other is efficiency. So let's focus on the uniformity first. And this is just a very basic model that we have here just to illustrate the point. So let's say we have a flat plate and we have two channels. Model that up, we simulate that, and we see a 24-degree variation across the part, which is a little on the extreme side. Maybe we add another channel in the center to cover that hot spot. Now we've got an 18-degree temperature variation across the part. Some improvement, but not quite where we'd like to be. So now we put 6 channels. Now we've got that temperature range down to 12, and you can go even farther than that. But the point is that the pitch, the distance between channels, controls that surface uniformity. And we can model up all sorts of different designs to see what's best, and we want to try to keep that temperature range as low as we possibly can. And then we have the depth, the distance between the channel and the part itself, part surface itself. This is going to control our core and cavity differential. And that core and cavity differential can play into warpage effects, of course. So with 6 channels here, we've got good pitch, but now we got to talk about depth. Are we the right depth away from the part? And in some cases, the design of the part itself is going to dictate how far away you can really get from those part surfaces. So you may have to be a little bit farther away on the cavity side than you are on the core side, for example. And in that case, you see a temperature differential build up between the two halves of the tool. And again, that can lead to warpage. So with poor depth, you see a temperature differential. With proper depth, you see that temperature differential go away. And it's not always going to be, right next to 0 there, but you get as close as you can, right? And then to my point earlier about warpage, you see even with a 5-degree temperature differential, you see that amount of warpage, and you improve that down to near nothing for a flat plate. So how do we improve cooling uniformity? Solution 1, add or move water. Solution 2 is to add higher conductivity inserts. Solution 3, maybe we go to conformal cooling. Conformal cooling is all the buzz these days, right? So just with standard conventional tooling, maybe we have a cooling design that looks like this. We've got a very tight piece of geometry here, very tight angle, and you see a temperature buildup in those corners way higher than the temperatures of the rest of the part. We do have a cooling line there, but we're not yet getting the cooling very close to that internal corner there. So we add some baffles, and we see that temperature drop from 244 down to 223 in this corner, 241 down to 209, out near the center of the part. So we see some improvement. That's great, but it's still a temperature that's too high, and we want to try to improve on that. So we look at the warp. We see, maybe 1.5 millimeters of warp here. We add the baffles, got it down to 1 millimeter, but we need to get it even better than that. So we improved by 33%. Let's see if we can get that even better. So we introduce a MoldMax slide. For those of you who aren't familiar with MoldMax, it's a beryllium copper alloy. Of course, it has a higher thermal conductivity than steel. So stands to reason that it's going to be able to pull heat out quicker. And that's true, but only if we have a cooling line that is in that MoldMax slide here. If we were to eliminate that cooling channel and try to just pull heat out with the MoldMax piece itself, what you'd end up with is a MoldMax piece that just heats up very quickly. So you always got to have cooling that's in the MoldMax or any other high conductivity insert when you choose to use one. In this case, so without the MoldMax and with the baffles, same as the previous slide, now we are able to drop the temperature some 70 degrees in this area and same in this area. So not only were the baffles good for us, but the MoldMax inserts were as well. So very beneficial to add both the baffles and the MoldMax. So whereas we started with 1.5 millimeters of warp in the original design, now we're actually warping in the opposite direction, but the magnitude's only 0.28 millimeters. So we're in a much more acceptable range of warpage, and we did a lot of good things with the cooling there, all with conventional tooling. But what if that doesn't work? What if we need something a little more complex, I guess you could call it? We could go to conformal cooling. So rather than using a conventional baffle or bubbler in this type of geometry, for example, you can design conformal cooling so that you can get these cooling channels even closer to the part surface. You know, with conventional designs, it's often difficult to get those cooling channels so close to the surface. And remember, when we talked about depth of channel from the surface, depth controls you know, a lot of that temperature variation that goes on. So oftentimes when you get closer depth, you have to put the cooling channels a little closer together, or else you get that temperature variation that you don't want. So here's a case study for a propeller fan. We've got a single cavity mold. We've got tight core side geometry, and we got thick walls in the hub. So we look at a conventional cooling design, and you can see right in this area here, we can't get these baffles real close to the surface. You can make an argument for maybe angling these and sticking them up there a little bit closer, but by and large, this is difficult to get close to those side walls up in these pockets all the way up to the top of that core. So, and it's also on both sides of the tool, core and cavity, it's difficult to follow the blade contours. Anybody that's molded fan blades knows that, you know, tolerances on those fan blades are often very tight. So we have to make sure that we have as uniform a cooling as we can possibly get. So here's a conformal cooling design idea. You can see we have cooling lines to conform to the part surface geometry, particularly in the fan blade areas. We're able to reach the deep core areas a little easier than we could with the conventional cooling. We added cooling to cool the sprue. You see a very tight helix coming around that sprue. And, you know, if you have a big, thick, fat sprue feeding your part, then could very well be the case that sprue controls your cycle time, and we don't want that. This was a design, just a little shout out to HTS for their particular type of conformal cooling. The way they do this shows a complex conformal cooling arrangement. They've been around since 2015. It's called metal fusion technology. They do diffusion bonding of pre-machined layers of tool steel, which is good because it's got the mechanical properties of forged tool steel. You know, when you 3D print conformal cooling inserts, those don't tend to be as structurally sound as, you know, a solid block of steel. And this also allows for larger cooling channels, which is good as well in those cases where you can get them to be larger. So we look at the results of conventional versus conformal. And what I did in this case was ran the cooling time out until we got similar temperature results in both of the designs. So on the left, to get the temperatures where they are in this cross section took 90 seconds. And on the right, to get that same 295 degrees in that thick section there, took 62 seconds. And notice also what happens here. You've got much more uniform cooling in this area than you did in the conventional. Look, there's a 191 up to 231 degrees as you go up the core here. That's a 40-degree variation. Here we've got a 4-degree variation. So clearly a better and more efficient design on the right. So better parts could be expected and a much lower cycle time could be expected. So that's cooling uniformity. Now let's talk about cooling efficiency. And now we're going to look at the cooling lines themselves. And 3 questions you really need to ask. Do I have turbulent flow? Are the cooling lines sized properly? And do I have proper circuiting? So let's look at a design where maybe we don't have turbulent flow. Turbulent flow is more efficient heat transfer. You know, when coolant flows in a laminar fashion, it kind of sets up layers through the cooling line that are a barrier to heat transfer. With turbulent flow, it's kind of a mixing type of idea where it allows that heat to move you know, laterally across a cooling channel much more efficiently. So in this case, you know, we've got laminar flow, very low Reynolds numbers. Reynolds number is a number that tells us whether or not we're laminar or turbulent. And for that, you know, it took 67 seconds to reach the temperatures that we wanted. And we get a relatively high temperature variation across that part for this design. And you could argue maybe moving some cooling channels around would be beneficial, but this mold was already built. And then we looked at turbulent flow, you know, moving that Reynolds number up to a much higher threshold. And for that, we were able to bring the cycle time down by 7 seconds with a lower temperature variation across the part. So in this case here, maybe you have molds that you work with that are high cavitation. Here's a look at you know, a quadrant of a 64 cavity mold. And initially the design had very restrictive bubblers in there. Some of you may call those cascades if you live in Canada, but we'll call them bubblers. The parts themselves are very small, you know, 0.8 inches in diameter. A very fast cycle is required. And, you know, by sizing things right, there was a potential on this to improve your earnings by about $183,000 on this. So, you know, either buying the software or using us to do analysis pays for itself very quickly on that. So these are different stages of flow based on the Reynolds number that I mentioned earlier. So, you know, laminar flow is when Reynolds number is below 2300. You see, we have a very restrictive flow coming back on the you know, return of the bubbler. The yellow area there is the feed. The blue area is the area between the tube and the drilled channel. You can see that's very thin. So that was the original design, and the Reynolds number was predicted to be extremely low. So low flow through there equals inefficient convection or poor heat transfer. We also have a transition area where things go from laminar to turbulent, but they haven't quite reached turbulent. Also, it's inefficient. It gets a little bit better, but you know, you see we've tried to increase the diameters here, but oftentimes it's about matching, you know, the effective flow area, what we'll call the hydraulic diameter of the annular tube on the outside versus the feed channel on the inside of the tube. And then we go to a just barely turbulent scenario. So this is very efficient convection. That says laminar flow, but it should say turbulent. So anything above 4200 is turbulent, And generally speaking, when you get above that threshold, you get kind of diminished returns. The heat transfer coefficient kind of levels off, and it just costs you an awful lot more water just for very small gains in the heat transfer beyond that 4,200 threshold. So how does this impact cycle? So in the laminar case, took us 7 seconds to get to the temperatures we wanted on that. When we match those temperatures with a condition where we are in the transition region between laminar and turbulent, we dropped that down to 5.8 seconds. Nice gain. And then when we went full turbulent, again, that should say turbulent flow, we were able to get it down to 4.9 seconds. So if you do all the math on that and calculate return on investment and so forth, you know, we came up with about $183,000 in savings for that particular mold per year. So that's turbulent versus laminar flow. Now we're going to talk about circuiting. You know, you look at this cooling design on this instrument panel and you say, whoa, how do we, I don't even know where to start. So, and you've probably seen it at the press, you know, just start jumping hoses together and see what happens, right? So this is an IP carrier. It's a very large mold with many cooling lines. And we're able to, through proper circuiting, maintain temperature uniformity with fewer GPM, but we got to do it right. And the potential savings for this per year were something on the order of $206,000. So what does proper circuiting mean? It means a moderate temperature rise. So if we were to just take every single cooling channel and have an inlet and an outlet for that channel without circuiting it together with any of the others, we'd get less than a 1 degree temperature rise. You know, we all pat ourselves on the back, and you know, that's great, but we can't. It's not practical, and you'll see why in a minute. Or you know, maybe we go to the excessive circuiting route. You know, this is kind of like Goldilocks and the Three Bears. This is too much circuiting, or not enough circuiting rather. You know, the one in the center is too much circuiting, and we get a temperature rise from, you know, one end of the channel to the other of you know, greater than 5 degrees. In this case, it's almost 14, but we look for numbers that are above 5 degrees temperature rise to say they're good candidates for looping with other lines. So, and now we've got the situation that's just right. So proper circuiting, temperature rise less than 3 degrees. You know, we've selected channels to go together to make use of cooling efficiency, and we've maintained our temperature uniformity. So here's the reason. It's, you know, oftentimes you just don't have enough GPM available at your mold to be able to do, you know, single in and out for every circuit. 134 GPM on that one. You know, a lot of people, you know, put so many lines together, it doesn't require many GPM to get turbulent, but we had that temperature rise, right? But with proper circuiting, we got cooling uniformity, and we were able to do it at a reasonable number of GPM. So that's the reason that we want to look for opportunities to pair the right channels together. And here's what it looks like if you have proper circuiting versus improper circuiting as far as the temperature is concerned. So when you have no circuiting, you know, every line is its own individual in and out. You have very uniform cooling. You know, you look for your hot spots, try to mitigate those hot spots if you can. Maybe you do all those things, move channels, use conformal cooling, use cooling inserts, mold backs, etc. When we go to proper circuiting, you see we've got this pretty much the same temperature uniformity as we did when we had no circuiting. But remember, now we're more efficient. We can do it with the GPM that we have available. Here's what happens when you do improper circuiting. You know, we get that temperature rise in those cooling channels, and now it's starting to affect the part. You see, you know, a lot of these areas of the part much hotter than they were in these other cases where we had proper circuiting. So if we decided to go with the single channel approach, rather than circuiting properly, it would take us an extra 20 seconds to get down to the temperatures that we had when we had proper circuiting. So, pick your poison on that. Do you want non-uniform cooling, or do you want a longer cycle? Those are the consequences of not doing proper circuiting. And again, you just don't know, until you start molding parts. If you're just randomly grouping lines together at the press, you really don't know what's going on in that tool. Okay, so those are the fundamentals, right? It's all about uniformity and efficiency, and those things can be carried over to other different types of Moldflow cooling capabilities. I'll mention a few here. We're not going to go through all of these in depth, but we will a couple of them. Now, the first one is CFD coolant flow. We'll talk about that in a second. We have two-shot cooling. We have transient cooling. We have induction heating, and we have rapid heating and cooling. All of these different types of cooling analysis, we'll call non-conventional cooling, are able to be simulated in Moldflow. We'll tackle the first three here. First one's CFD coolant flow. CFD stands for computational fluid dynamics. Why does that matter? It's really boils down to the modeling of the cooling channels. Most cooling channels look like little beams, and those are, in a standard Moldflow analysis are modeled with what we call beam elements. But what do we do when we have an odd-shaped cooling circuit like we see here in this cup mold? You have an inlet here, and now we have this cooling jacket around the cup, and we have an outlet here. Well, we can't really model that properly with what we call beam elements, so we have to model it in full 3D, and it's an irregular shaped channel, and this is used a lot in conformal cooling. You have an odd shaped part, and you're trying to conform the cooling channel to the shape of the part. So sometimes you have to go to an irregular shaped channel, and in those cases we have to use this modeling technique. But again, it's no different. The objectives are still there. We still need uniformity, and we still need efficiency. It's just a different modeling technique. And here you see the velocity of the flow. You can kind of see the flow squirting down to the bottom and then kind of backing up on itself in that case. And that's not something you'd be able to simulate with the conventional Moldflow cooling. Then we have transient cooling. One thing you should know about Moldflow cooling analysis, the standard analysis, is that they are cycle average temperatures. What does that mean? So if you were to pick a couple of spots on the mold like we see here in the upper right-hand corner, we have a blue spot and we have a red spot. The blue spot's on the part surface, or on the mold surface rather, of the core, and that red dot is buried 5.3 millimeters below. So it's tracking the temperature through time for one cycle. So it starts here, as hot plastic comes in, that temperature increases, and then it gradually cools over time. Same with the red. And if we were to average all those temperatures, you see the blue line here for the blue dot, and the red line, of course, for the red dot. Those are the average temperatures. These average temperatures are what Moldflow is actually reporting when you do a standard conventional Moldflow cooling analysis. And you say, well, okay, I want it all. I want all this. Well, as is the case with any simulation, it's always a balance between solution accuracy and time spent. So these transient analyses not only take more time to set up and run, but they also take a lot more time to solve. Good, bad, or indifferent. If you have the time and you can do it, this is perfectly reasonable. But notice the difference in temperatures between the average temperature and the end of cycle temperature. It's not that great. Some cases you'll see larger differences, but in many cases, the conclusions you draw as to where to put the cooling lines, how to run your cycle, how to circuit properly, all of those things that we mentioned really don't change a whole lot. So there are many cases where this is very beneficial, where you need a lot more accuracy to know what these temperatures are at the end of cycle or at any point during the cycle. But But generally speaking, this would be more advanced analysis that isn't totally necessary on most of your molds. So that would be a single cycle transient for one cycle. The assumption there is that we've reached steady state. But what if you need to know how many cycles it's going to take to have your production start up? You can also do a transient analysis from production startup, and this would track these same temperatures, but we would start at, say, room temperature and see how many cycles it takes for us to reach steady state. And you can kind of see things leveling out right in this area here. So again, more advanced analysis, much more time consuming and so forth, but there are a lot of good things to gain from that as well. We also have two-shot cooling. This isn't something we used to be able to do in the past. We used to have to kind of make some assumptions and model the first shot as what we would call a part insert, but now we can actually use a transient analysis to do two-shot cooling. So this is where the temperatures of the first shot cooling analysis would actually affect the second shot. But again, same objectives as standard cooling. You still want uniformity, you still want efficiency, but now we have the ability to marry the parts together in simulation. So we do a full 3D analysis with transient cooling. You know, we have a first shot over here, we have a second shot over here, molded over top of that. You know, we have heat transferring from shot 1 to shot 2 and vice versa. And this gets a little deep into the woods, as you know, if you're an analyst, but you know, you have to define things a certain way in Moldflow to get this to work properly. And this is just a kind of a snapshot of how this plays out. So if you track the temperature of the mold in the first shot cavity, that's how that looks, and then here's how the second shot cavity plays out. And here's just an animation of that over time. So cavity view on the left, core view on the right. You can see temperatures fluctuating as the cycles run through. And then you can also look at that from a cross-sectional view as well. So, you know, the topic of this webinar was what's best for you. And I would argue that all cooling analysis will give you some type of opportunity to improve. It's going to give you better parts. It's going to increase your profitability. And, you know, this is true no matter what type of cooling analysis you're doing, whether it's, you know, the CFD analysis, the 3D transient analysis, you know, induction heating, rapid heating and cooling. Do analysis. It's going to ultimately give you better parts and increase your profitability. Right, and it doesn't matter what type you're doing, temperature uniformity and coolant flow efficiency are king. These two things need to be met no matter what type of analysis you're doing. So how do we do that? How do we solve that problem? Just to reiterate, so for cooling uniformity, you can add or move water. You can change out steel for higher conductivity materials, or you could use conformal cooling. So and that's not just a cooling uniformity thing. These things also lead to more efficiency as well. You know, profitability increases when you have higher conductivity materials. Profitability increases when you get cooling channels closer with conformal cooling. But the other side of that equation is you better make sure that the channels that you have turbulent flow, that you have sized them properly, and that you have circuited them properly. So here's some general ideas. So make sure you plan ahead to have Moldflow cooling analysis done proactively. You know, don't wait till you're ready to cut steel on a mold to do this. By then it's often too late, the clock's ticking. So, you know, make this part of your everyday activity when it comes to designing and manufacturing molds. If you have say in that cooling design, you should be talking about Moldflow on every one of them. And again, have this done at the earliest stages of product development. You know, if you're waiting too late, there's not going to be any time to try a bunch of different scenarios out, and much less get them implemented. Here's some specific ideas for molders and OEMs. So insist on Moldflow cooling analysis. Do it yourself or use an outside source. We can help you in either case. We sell the software, we train engineers, and if you're on the learning curve, we can help you along with that. We can mentor your analysts. Know your GPM. I find this out a lot. I've gone to a lot of mold trials, not recently with COVID, of course, but a lot of times I go there and I ask them, how many GPM are you putting through this mold? And I'd say at least 90% of the time, they don't have a clue. No idea, they're not measuring it. And do the math. I mean, what does X seconds of cycle savings mean to you? You saw some big numbers that we calculated, based on some assumptions earlier, $183,000 a year, $206,000 a year. That's huge. Maybe it's only $10,000 a year, still worth it. For part designers, when you're designing your parts, avoid difficult to cool areas where you possibly can. Much of the problems that result on the manufacturing side for injection molding result from the part design itself. Follow those plastic part design 101 recommendations, and this is one of them for cooling. Try to avoid difficult to cool areas wherever you can. And then, of course, use analysis to identify those areas. Everybody, in my opinion, should have some level of Moldflow on their desktop, even if it's just the Moldflow Advisor. Put that on your desktop. You can identify, if you're a part designer, you can put your part design in there, very quickly identify what would be a red flag in terms of cooling. For mold makers, be creative and test different designs using analysis. Don't settle for just good enough. Be creative and test those ideas, and use those cooling suggestions from analysis. So those are just some general ideas and some specific ideas. What's new here at CAE? We will be at AmeriMold here in Chicago, September 21st through the 23rd. I will be speaking. If anybody's interested in the topic of windage, if you've ever heard of that, I will be talking about windage on September 21st at 11 a.m. This is not new, but we've been with Autodesk as a partner for now 2 years. We provide software training and mentoring, of course, for Moldflow. We do a lot of learning activities. We call it building expert analysts. I mentioned training. We're back to in-person training, thank goodness. Training is so much better in person when you have that opportunity. So any Moldflow users out there that are looking to get trained and maybe make your way up to expert analyst status, give us a call. Of course, we have the Ask the Moldflow Experts webinars. Look for our next one. I believe it's in September. You can find that online. When we have these signups for these webinars, we give the opportunity to ask questions. And a lot of the questions I went through that I saw have a lot of very specific Moldflow based, how do I do this in Moldflow kind of a question. Moldflow office hours is a perfect opportunity for you to learn more about those in-depth things. So what you can do is sign up for 2-4 hours, whatever, of my time or one of my engineers' time to go through very specific types of subjects like that. And I mentioned our website earlier. You can also follow us on LinkedIn. So now for those questions and answers. I took some of the questions off of the sign up. And I'm going to start, gotta hide some things here. I'm going to start with one of the funniest questions I got. Do you think you know more than I do? And he puts an LOL behind it. So I'll leave that up to you. We do these Ask the Moldflow Experts, and I think we provide a lot of knowledge. So I don't know if I know more than you do. but I hope that what we've presented today is very helpful to you. So just thought I'd start off with a funny one there. Next one. So when exporting a windage model, is cooling optimization required? So, windage is a very in-depth topic, and I won't go into too much depth here, but one of the things we preach with windage all the time is to make sure that you've taken out as much warpage as you possibly can before you A, decide on windage, B, actually do it. So windage becomes a lot more difficult. Morphing the part becomes a lot more difficult when there's more warpage. So, to the extent that cooling is causing a fair amount of warpage in your mold, then yes, you absolutely ought to optimize cooling before you do windage. So a lot going on when it comes to windage, and you want to take as much warpage out of there as you can. And when you're providing efficient, uniform cooling, you're going to put yourself in a position to take a lot more warpage out of there. So absolutely. Next question is, what is the confidence level for correlation of cooling analysis to actual tool temperature? So, I mentioned earlier the difference between cycle average numbers and transient cooling numbers. And that's where one of those areas where a lot of it depends on how you go about measuring things. So first of all, in the analysis world, the transient cooling analysis is going to give you numbers closer to reality. And secondly, when you go to measure tool temperatures, for example, there's a time lag between when you open the tool and when you take measurements. And there's different ways to measure things, right? You can use a pyrometer, you can use an infrared gun, surface emissivity of the mold can play into this, but there are ways to get more accurate. But by and large, measuring tool temperatures is going to be an exercise. I don't want to use the word futility, but you ought to look more at trends than you look at the actual numbers, because it's just very difficult to get into the tool and measure them properly across the tool. So look at trends, and usually those will show up very nicely, very accurately. When you compare it to Moldflow cooling analysis. My friend John Bruner over at DSM Engineering Materials asks, some discussion on equipment capability would be helpful. Default simulations use 10,000 Reynolds number for each circuit. What are the typical scenario strategies? That's absolutely true. There's different ways to impose the coolant flow on the channels that you design in your simulation. And one of those ways is to just say, make everything a certain Reynolds number, because if we want turbulent flow, we want it at a certain Reynolds number. That's one way to do it. The problem with that becomes now you have different pressure drops across each circuit, because it's going to enforce a certain amount of flow, and it's going to calculate a certain amount of pressure to get to that flow. In reality, in a mold, most of the channels are hooked up to a cooling manifold or directly to the thermolator, or the pump, or whatever it is. So the way molds really work is that there is plus or minus a little bit, essentially equal pressure drop across each circuit when they're hooked up to manifolds. So that's the way I like to run analysis, is find out what kind of pressure drop I need, and then apply that pressure drop across each circuit. Next question. What are the benefits of cooling FEM over cooling BEM? Okay, so this gets, again, a little deep into the woods, but essentially what he's asking is there's the two different methods. We have the cycle average, that's the cooling BEM or boundary element methods, or cooling FEM, finite element methods. The FEM is the full 3D transient cooling analysis. I mentioned some of those benefits earlier. If you want more accurate at the end of cycle temperature numbers, then cooling FEM is the way to go, but it's going to cost you time, more time to build the model, and more time to run the model. Okay, next question is how to determine ideal GPM for my molds. What is better, temperature or GPM for reducing cycle times? Having problems reducing cycle times, all extra time is cool time. So You know, this is something that's been studied at length in terms of, you know, should I focus more on the water temperature or should I focus more on GPM? I think GPM is going to get you better cycle times than just reducing temperature of the cooling lines. And if you listen to Mike Seppi, Mike is a you know, he's a consultant. He writes a lot of articles for plastics technology. He will argue every time for higher mold temperatures to induce crystallinity so that the part can actually be ejected a little bit earlier. And that also affords you the ability to run lower melt temperatures so that you can improve cycle times that way. But you know, you can do it both ways. You know, but GPM is where you're going to get probably the best bang for your buck in terms of improving cycle times. Next question is, how will Moldflow assist the designing of conformal cooling? Well, Moldflow is really there to analyze, you know, which ones work and which ones don't. So, you know, obviously it's not going to design the conformal cooling channels. That's up to the mold maker, mold designer. You know, we can certainly assist in designing those channels, but ultimately, you know, the shape of those channels and the pitch and depth and where they're located, that's going to come from a little bit of a trial and error process in Moldflow itself. So that's really how Moldflow assists in doing it. Can you demonstrate how you import conformal cooling circuits for analysis? That's really a straightforward thing. You know, whatever CAD system you design your cooling channels in, it's a pretty straightforward import into Moldflow, and then you mesh them there in 3D through all the standard methods that you use to mesh in 3D. So that's how you import. It's a pretty straightforward process. So good CAD practice, good clean geometry in whatever CAD system you have will generally import rather easily into Moldflow. So that's about it for the question and answer session. I want to say thanks again to everybody that attended. We really do appreciate your time and attention. Again, look for more of these webinars. If you have any suggestions for topics, you know, feel free to email me. You know, always like to see what everybody's eager to learn out there when it comes to Moldflow. So we hope to see you in September. Hope to see you at AmeriMold and at the online on the next webinar. So have a great day, everybody. Take care.